Hello everyone, welcome back to my channel. So today I've kind of made like a so-called selfish video just because I don't even know why I'm saying this on this video, but basically I slept at 5 yesterday because there was this like droning noise from one of the machines around my room. So I'm not feeling great to study right now, but I just felt like it'd be good to just revise the Lagrange method because we do this in intermediate microeconomics at UEA, and I might forget how to do it, but like essentially the Lagrange multiplier helps find the optimum point of, in this context, labor and capital for a production function, sorry, and it does it by optimizing it subject to a constraint. So I have a question here which essentially says firm's production function is Q equals square root of L multiplied by square root of K. The firm has a unit of capital which is fixed in the short run, but it's not really applied to us in this case because we're trying to find it in the long run. So capital is variable, and the cost of labor is 1, and the cost of capital is 4. And the firm has received an order to produce 100 units. So use the Lagrangian to solve the cost minimization problem and identify the optimal choice of inputs in the long run. So essentially what you want to first do is find what you're trying to minimize or maximize, because this is an optimization question. It's one or the other usually. So find simple as I've got horrible handwriting right now, but that's fine. So find what you're trying to optimize. So in this case, from the question, we can clearly see that we're trying to cost minimize. It's a cost minimization question. So what you have, there are two parts of the Lagrange multiplier. So you have your objective function, which is essentially the part that you want to minimize or maximize. And then you have your constraint part, which is the bit that goes within the lambda. So that could be anything from the production function, or in utility it could be the costs and things like that, right? So it really depends on your context, but depending on what you want to find, your objective function will change and your constraint will always change. So in this context, we're not trying to find production maximization, we're trying to find cost minimization. So our objective function will be the cost function, right? Because that's what you're trying to minimize, because that's what the question says. And then our constraint will obviously be the production function, because that's the only other thing in the question that we're provided. So once you've done that, you can basically just write out your cost function. So as we can see from the question, we are told that the cost of labor is 1 and the cost of capital is 4, and we've been also given that labor is stated as L and capital is given as K. So what we can do is write that as an equation. So the cost will equal to basically L plus 4K, which can also be written as 4K plus L, but it's the same thing. And then our production function is Q, which equals L to the half, K to the half. But we are told that the firm has been ordered to produce 100 units from the question. So because we've been told that it's 100 units, Q is 100. So 100 equals L to the half and K to the half, and then that's step 1 done. And then part 2 would just be essentially as L, or Lagrangian, equals the objective function plus lambda of the constraint, right? So once you've done that, you can write the Lagrangian equation or function, which just equals L plus 4K plus lambda. And for the constraint, you want everything to be on the one side, because you're trying, this whole thing is a constraint, and you can't put an equals within an equals equation. So you just bring this to one side or this to that side. So just for our lives to be easier, I'll just do 100 minus L to the half multiplied by K to the half. And now we have everything within a constraint on one side, which is just equal to 0, right? So once you've done that, you basically write out your first order conditions. So what you want to do is essentially do the partial derivative of with respect to L and with respect to K and with respect to lambda. So what we get is the partial of L equals 1 minus a half lambda L to the minus a half multiplied by K to the half. Notice that this is all one part, so that's why the K is there and it's considered as a constant. And then with respect to K is 4 minus a half lambda L to the half K to the minus a half, right? Because again, with respect to K, they're together, and because L is multiplied by it, L is held as a constant. Then with respect to lambda, it's just basically the constraint function. Should know this by now. And you set all these equal to 0. The reason why is because in an economic practice, we assume that all resources have been allocated and nothing's been left or held within the reserves. So basically, all the costs will be allocated to either labor or capital, which is why it's equal to 0, because you've got nothing left, right? You've got no resources left. And then once you've done that, basically solve for L and K. So basically solve the simultaneous equations. And what we can do is do the Lagrangian of L divided by the Lagrangian of K. Essentially what this does is it eliminates the lambdas, so then we can find the ratio between L and K. So what we get is something like a half lambda L to the minus a half K to the half equals 1 all over a half lambda L to the half K to the minus a half equals 4. Right, so all I've done here is I've simplified it quickly. So I brought this and this to the other side so it becomes positive, and then I just divide them together, which is how I got that. And you can see here the halves cancel, the lambdas cancel, and then using the power rules, you can get the L to the power of minus a half minus 1 over 2 is minus 1, and then K to the half minus 1 over 2, which becomes a half plus a half is K to the power of 1. So you simply can put it as K over L equals 1 over 4. And what we get there is the 4K is equal to L. And once we've done that, that's not the final optimum point, even if there was just letters or like algebra being used, because you still got a K and an L, which is not what we want. So what you can do is further solve it by using the lambda equation by substituting, let's say, L is equal to 4K in here. And what happens is you get 100 minus, so we're substituting L as 4K, so it'll become 4K to the power of a half multiplied by K to the half, which equals 0. And then you have 100 minus, so square root of 4 is 2, because to the power of a half, and then remember to multiply everything by the power, so it becomes K to the half as well, multiplied by K to the half, which equals 0. And then you can bring this to the other side, and this basically becomes 2K, because a half plus a half is 1, because you're multiplying the bases together, and when you multiply bases together you add the powers, and this equals 100. So therefore we found that K star is equal to 50, right? So once you've done that, you can then resubstitute it back into this equation over here, and you get that L star is equal to 4 times 50. So L star is equal to 200. So those are your final answers. If you're not provided with, let's say, like 1 over here and 4 over here, and you're provided with like alpha and beta, it's essentially still the same thing. You find the ratios and then you get an algebraic expression instead of numerical values over here. So that's how you find the optimized points or the optimal points using the Lagrange method. So hopefully this video helped you out, and I'll see everyone later.